So you might remember a little while ago we did a loop-de-loop problem where there was a car going onto a loop and the car had to go fast enough so that when it reached the top of the loop, it had an acceleration that matched the centripetal acceleration necessary to keep it on a circle, right? So we had that for the forces. So here's a sketch of a free body diagram. We had weight pointing downward, and we had the normal force by the track pointing downward. And the net force then had to be equal to ma, of course, and the a for something going around in a circle, if the acceleration is pointing towards center, is v squared over r. Let me just fix that right there. Okay. Now, the minimum speed occurs when you're going slow enough that the normal force reaches its minimum value, which is 0. In which case, we had that the weight, mg, is equal to mv squared over r, and this is the min speed at the top, and we got that that was equal to square root of gr. Okay. And of course, r is the radius of the circle. Now, we looked at this with a video where there was a car coming in, and it had a certain speed. And we calculated the minimum speed at the top, but we had not yet calculated the speed you need to enter the circle in order to make it. And so we're going to do that calculation now with energy. So our general energy equation is that the change in energy is equal to work. The energies that change, the speed of the car changes, the height of the car changes, and so that would be equal to the work. And remember that work is due to external forces. The only remaining external force on the cart is the normal force, and the normal force is not going to do any work if you're translating along the track. So that is also equal to 0. And so that means that the initial kinetic plus gravitational is equal to the final gravitational and kinetic. So this is going to be our final state up here, and this is going to be our initial state down here. And we can see here that if we set our coordinate system in the most reasonable way, where y is being measured from the ground, that the initial gravitational potential is 0. We can put in our equations, 1/2 mv squared for kinetic energy, and we just put in the final and initial for our values there. And you can see, of course, that the mass is all going to cancel out. We are trying to find the initial speed, so we can multiply by 2 just to make that a little bit nicer. So we get a vf squared plus a 2 gyf. Yf is the height when you reach the top, and that, of course, is just 2 times the radius. So we're going to have that vi is equal to vf squared plus 2rg. Now, if we plug in what we know from up here, is for our minimum speed when we get to the top, if we plug that in for vf, we get that we have a gr, it's 3gr, and so our initial speed necessary is, oops, I went ahead and added, I did it again. I'm not going to edit this. 2rg, so the total is 3gr. And this accounts for the speed that you'll lose as you go up the ramp.